So as we saw in the previous lesson, kind of at the end, that as we were calculating the area in between a positive function and the x-axis, that we were creating this idea of drawing several rectangles, of which we are then calculating the area of each rectangle, where this f of x of I star, or if we use the notation that I prefer, which is more in line with what we've been doing in the AP Calculus, that we are choosing a endpoint or a point in an interval, either the left endpoint, the right endpoint, the midpoint, or any one in between, and that we're using that to calculate the height of our rectangle. We're using delta x, that is our width of the rectangle, and then we calculate the area of each rectangle, and then we add up all n rectangles that we have, and that this summation is what we call a Riemann sum. And that those Riemann sums are approximations of the area that we were looking for. And then what we did after that is to say, well, I want to find the exact area. So we're using the calculus idea of applying a limiting process. We let delta x go to 0, which is the same as saying let the number of rectangles increase, so that it becomes a better and better approximation, and through the limiting process, the approximate area will converge on the exact area. And then we saw sort of at the end of the lesson last time that we used our calculator to calculate this, and we saw that in the calculator, this is actually a definite integral, that this must have something to do with the antiderivatives and the indefinite integrals that we discussed back in section 5.1. So in section 5.1, we had this idea that if I were to see something along the lines, the integral of f of x dx, that when you have this in that differential form, that when you are working backwards, this means to find the antiderivative, and that we would find a general antiderivative because there are many functions whose derivative would be the same because the derivative of a constant is 0. And remember, we're using this capital F mostly because we've already identified what's inside the integral as f of x, and that's where if I were to take the derivative of f prime of x, I would get f of x, that we have an antiderivative. The plus c takes care of all the family of antiderivatives. And so the fact that we're using a similar idea here, that I have my integration symbol, and the only difference right now is that instead of being indefinite, which is what we have up here, we are turning it into what's called a definite integral, that we are giving it bounds on this. That when we do that, that actually is directly related to these Riemann sums that you have over here. Now, the first thing that I want us to be kind of careful at is that this definite integral and this Riemann sum that we are calculating is not always the area between the function and the x-axis. That the first examples that we looked at were what I would consider to be really nice examples where our function was above the x-axis. And that we talked about kind of at the very end, but it was kind of quick because I was running out of time, but that at the very end, if I have a function where the function values are negative, that then we would no longer be talking about kind of a total area situation there, that if the function was always negative, you would have to then of course make it positive to get area. That we're going to have to kind of make some defining statements about what does this definite integral find, and what does it have to do with area. It's related to area, it is not always total area. A little notation before we move on to the first example. The a to b, you will remember that when we were doing this problem, the a to b is setting your interval on f of x. So this was f of x for an interval of a to b. This a is going to be called the lower limit of the integral, and the b is going to be called the upper limit of the integral. We're going to expand our knowledge about this a little bit in that while in the context that I was doing the examples earlier, A to B was always an interval, A was smaller than B, it's not necessarily true that A and B have to be A smaller than B. This could be, when we're looking at it, that could be 10 and that could be 5. That's going to be perfectly fine, and we're going to define what that is in this set of notes, what happens when the lower limit is a smaller number than the upper limit, or the lower limit is a bigger number than the upper limit. So we're really going to define and investigate in this set of notes what is a definite integral and how is it related to this area problem that we were doing in the last set of notes. Now, taking a look at this first example, I want to evaluate the definite integral from 0 to 4 of 2x dx. Now, looking at this, the first thing that I would do is this idea of let's sketch a picture. So I'm essentially looking at a function f of x, and it's a nice easy function, straight line with a slope of 2. But I'm only interested in this function f of x when you are on the interval from 0 to 4. So let's denote 0, and I'm going to come over here and denote 4. So when I look at this kind of region, it is related to area. That if I was going to take this integral from 0 to 4 of 2x dx and think of this as the limit as n goes to infinity of the sum I equal 1 to n of my delta x f of ci, that if I'm thinking of it as this is my definition of it, that regardless of what I'm choosing here, because the function is always above the x-axis, it is going to be talking about this area under the curve right here. So in this problem, because f of x is always positive, this definite integral is the area denoted by this yellow right here. Now, obviously, do I really want to do this the long way? Can't I pretty much geometrically, and when we say geometrically, we mean, hey, use geometry and basic knowledge in order to calculate what this is. Once we recognize that this integral from 0 to 4 of 2x dx actually is the area under y equal to 2x from 0 to 4, and then I recognize that that is nothing more than a triangle area, that I'm not going to worry about doing things a long way and use the limit definition and do anything like that. I'm going to be like, I know how to calculate this. I can calculate this by doing 1/2 of the base times the height, and then I just do some calculations. My base in this is going to be 4. And then if I were to calculate the height of this section over here using the function, I would get at 4, the y value is 8, so it's going to have a height of 8. And so I can see that I'm going to have an area of that triangle of 16. So what I know is I basically have evaluated this definite integral using easy geometric concepts in order to find out that the answer is going to be 16. Now, of course, we can verify this on our calculator, so we're going to use the function int command, and then just remind you, old calculators, I would put 2x, x, and then 0 to 4, and on the new calculators, you're just simply going to fill in just like what it looks like here in our definite integral. And we'll just verify to ourselves that it is going to be our 16 that we've got, just to show you what's going on. So I'm going to do 9, and this one's easy enough to type in, 0 to 4, and then my 2x, and dx, my change in x, and then we enter and we get 16 as expected. Okay, and so the idea here is to recognize that in this situation, because f of x equal to 2x from 0 to 4 is positive, so because f of x is greater than 0, greater than or equal to 0, for 0 to 4, this definite integral was exactly the same as the area under the curve from 0 to 4. Now, let's talk a little bit more about this area under the curve. That when we're when the function is non-negative, so greater than or equal to 0, and integrable. Now, what we mean by that is that it can be integrated, that the function that is in here, and we're going to talk more in detail about this later, but this function 2x is the derivative of some function that we can find. Okay, that's what we mean by integrable, that it must be the derivative of some antiderivative that I should be able to find. And if basically in this problem, kind of taking a look at this, we can say that is 2x the derivative of something? Using your knowledge in 5.1, what would 2x be the derivative of? It would be the derivative of x squared. So it is integrable. I can work backwards over this closed interval, and that we know that this definite integral is going to be equal to the total area for a to b. Total area under f of x, which we mean between f of x and the x-axis, from a to b. And that will be true. Now, when we have a function that is always negative and integrable on the interval, that basically means we have a situation where our function from, say, a to b, if it was 0 to 4 like it is above, now the function is always below. So when we calculate this definite integral, right, because we're doing a sum of areas of rectangles where we're getting the height of the rectangle from the function value, when you see that your function values are all going to be negative in this situation, the definite integral itself is going to be a negative value. And so if I want to actually find area which is always positive, I have to do the opposite of it in order to get total area. So it's only equal to total area under f of x for a to b if you take the opposite of the definite integral. So that's the first thing, that the first key idea here is that while the definite integral and area are related to each other, they are not always the same thing. If the function is non-negative, then the definite integral and the total area are the same. If the function is negative, then it's going to be the opposite of the area, because area is positive. You have to take the definite integral, which will be negative, and make it positive to say that that's the area. So you can use the definite integral to find your total area under the curve, or between the curve. I guess technically when you say under, that might be a little confusing. I should probably be saying more along the lines of the area between f of x and the x-axis. It's okay to say under here because that makes more sense when it was above, that under means between the curve and the x-axis. Now, most functions, however, don't come in where they're always above and they are always below. All right, so this is just summarizing what I just said, that the definite integral does not give us area because area is always positive. But let's talk about this idea, kind of a new phrase that we want to talk about, which is accumulation of area. What do we mean by accumulation of area? So you want to think of accumulation as kind of like a net difference, that you've added a certain amount of area to your function. And when I add that certain amount of area in, I'm accumulating area. And it's like the difference between what I used to have and what I currently have. Now let's kind of go back and let's think about this accumulation idea with the example that we were doing here. Because we know what the antiderivative is. We think of this as a velocity curve. And if I have a velocity curve, maybe the units of this velocity curve are going to be in miles per hour, just as an example, trying to put some context here. And so my x-axis is going to be in units of hours. And then when I calculate this area that we are talking about, the area is now going to have units of your 4 hours times your 8 miles per hour. You're going to basically have units of miles. So this accumulation of area, if we're talking about this in terms of velocity, like these units, is an accumulation of distance, which is a displacement. Remember when we talked about that when we had a position function, and then we had a velocity function, which is the derivative, that if I were to look at the position function, that we would know that when the velocity was positive, that meant that my position was increasing. I was accumulating distance. When my velocity is negative, I am decreasing from my position function, which means I'm losing distance. So I gain distance and I lose distance. And so in this idea, when this is talking about a net accumulation, let's think about the original function. So we're saying our velocity function is 2x. So my position function must have been x squared. What was x squared at 0? It was 0. So let's just do 0 and 4. What was x squared at 4? It was going to be 16. What is your net accumulation, your displacement in your position? I gained 16. But notice x squared may not be the only one that you had. It could have been x squared plus 1, right? Because the derivative of x squared plus 1 is also 2x. Well, even if I'm doing this scenario where it's x squared plus 1, if I take a look at the values, so I'm going to erase that and come back in with the values now, at 0 it would have a value of 1, at 4 it would have a value of 17. My accumulation at a time 0 to 1 is 16. My net difference is 16. So the idea here, and kind of the big idea of this section before we actually get into the meat of calculating these, is that this definite integral is an accumulation of area. That it's actually finding, and in the example I'm using, this is your velocity function, so this is giving your displacement. We simply call it accumulation of area because you may not always be looking at a position function. The area that you have, you would figure out whatever the units are, and it's an accumulation of, shall we say, quantity, of whatever your quantity function was. F of x is your rate function, and your rate function is telling you how much you have accumulated over the interval a to b, how much you have accumulated of that quantity over the interval a to b, and that quantity is always area because you have a rate, which is going to be your quantity per time, times your time, and so area is always quantity. So it is an accumulation that we are looking at. And so when we are doing the definite integral, we have to recognize the definite integral is not going to give us total area between the curve and the x-axis when the curve is both positive and negative on the interval. It is only total area when it is only positive. So when we're looking at this idea, the area of all three of these regions is positive. However, the definite integral for the region from -5 to -2 is positive, from -2 to 3 is negative, and then this one would be positive. So the first thing is that you have to try to recognize, if I ask you to calculate these definite integrals, how are they related to the area that you see? Are they going to be positive values or are they going to be negative values? If I was to create a definite integral from -5 to 5 for f of x dx, this is not going to equal the total area that you see. It is going to be an accumulation of the area, that it is not total area. So we're going to gain some when the velocity is positive, we're going to lose some when the velocity is negative, and then we're going to gain some again when your velocity is positive again. And so the idea is, how would I know whether this is positive or negative? We could determine that by kind of paying attention to, we've accumulated we lost some and then we accumulated some more. It looks like we've gained more area than we've lost, so it probably will end up being a positive net that we have. But that's something that we want to pay very careful attention to. All right. And also thinking of this, as our velocity or our rate curve that's allowing us to accumulate. Now the second half of this is that notice I'm working in time from beginning to end. As time passes left to right, I accumulate, I lose, and then I accumulate. But there's a different perspective here on this that we don't always integrate from left to right. Sometimes we're going to go from right to left. We're going to go backwards through the region. Backwards. Think of it almost like backing up. Instead of accumulating, we're going to take it back out because we're going backwards through the interval. We're kind of putting it in reverse. So if I had up here filled it up, took a little out, and then filled it up some more, if I go backwards, put the video in rewind, it will take it back out, put it back in, and then take it back out again. So that you'll notice that when this goes backwards, and we'll know we're going backwards because the lower limit is smaller, or the lower limit is a bigger number than this limit. We went 5 to 3, 5 to 3, I headed backwards through the interval. So what used to be a positive accumulation because I'm going backwards is now a negative. I'm taking it back out. That's what you want to think about here. Another way to think of this is if we're doing our delta x going backwards through the interval, right? Then we would be going a minus b over n, but this ends up being less than 0, and then we take n and we let n go to infinity like we did before. So you end up, one sort of way of thinking about this is that your delta x, because you went backwards through the interval, is now a negative number instead of a positive number, and so it'll be a negative times whatever f of x is, so it ends up being the opposite of what it was originally through the interval. Okay, so a couple of notes that if I want a relationship between this, if I go forwards through the interval, the value of this, if this is positive, then the value going backwards will be the opposite of that. And so this part would be a negative, and then I have to multiply by a negative to make them equal to each other. That going forwards is opposite of going backwards through the interval. Okay? And so we keep that in mind. That's going to be something that we're going to use as we are discussing the area, the accumulation, and this total area or the displacement that we're going to be looking at. So the accumulation is like your displacement. Your total distance is like your accumulation. How much, sorry, I'm getting my own self switched around here. Your accumulation and your displacement are the same thing. If I want total area, I need total distance traveled. So you're going to have to adjust what you're doing. You can't do an integral on this problem from A all the way to B, from -5 to 5 to get total area. You're going to have to split it and do -5 to -2, and then you're going to have to do -2 to 3 and then make it positive, and then do your 3 to 5. So you're going to have to split it up. Alright, so we get the idea that definite integrals will help us find area. Area will help us find definite integrals. That's what this comment in bold here. But they are not exactly the same thing. We need to be very careful about what they're asking us to calculate. What are they getting us to find? So here's an example. Alright, so I'm giving you this function f of x shown below. Shaded here are two regions, and I have designated the area of those regions with the positive numbers a1 and a2. Alright, so those are areas. So a1 is positive, a2 is positive. And so I want to talk then about finding these definite integrals. Now, when I want to find the definite integral from -4 to -1, notice that my function is positive on this section. So when I go to calculate this definite integral, it will exactly be the same as the area of that section, so it will be a1. When I go to calculate the definite integral from -1 to 4, Now I have to recognize that my function is below. So the definite integral is going to be a negative number. The area is a positive number, so the definite integral will be a negative times whatever that area is. Because the definite integral is negative because the function is below. This definite integral is positive because the function is above. All right, now if I look at from 4 to negative 1, now notice that I'm going backwards. See, what happened before, I accumulated area and then I took some area out. Now that I'm going backwards, what I took out, now I'm going to put back in. So this is going to be a positive value because I went backwards and the function values are negative, and a negative times a negative is going to be a positive. So this would simply be A2. All right, now if I go negative 4 to 4, the first thing to recognize is that this is not total area. This is not going to be A1 plus A2 because it's not total area. This is our net area or our accumulated area. And so I gained some and then I lost some. And overall, if I had to guess whether this was positive or negative, by looking at how much I gained and how much I lost, my accumulation is going to be a negative value in the end because I have lost more than I gained. How do I find it though? I go, well, I gained A1 and then I lost A2. So that would be my definite integral from negative 4 to 4. All right, and then we take a look over here. This is just us playing around. We can calculate definite integrals over whatever bounds we want. So we've already figured this. This is just us playing around with it algebraically almost. From negative 4 to 4, we already got A1 minus A2. And when I go minus 2 times, a constant times does exactly what you would think. Minus 2 times, evaluate the definite integral from negative 1 to 4. Remember that is going forwards and it's below, so this would be a negative number. And then we just simply simplify, and this does end up being A1 plus A2. Now notice that in this, none of these, well, this one sort of represents the total area, but only more by happenstance. Let's talk about if I really wanted to calculate total area, what are some things that I could be doing to calculate the total area? I could take the integral from negative 4 to negative 1 for this function, because that's positive. But instead of adding it to the integral from negative 1 to 4 of f of x dx, what I'm going to have to do, because this is a negative number, is I'm going to have to make it the opposite of that number that we had. So that way it would end up being a positive number. And let's just check this out and show that it works. This integral was A1. This integral was negative A2, so A1 minus negative A2 equals A1 plus A2, my total area. Now another way of doing this, because there's going to be more than one way to look at these, you could have done for your total area, you could take your positive area, negative 4 to negative 1 f of x dx, and instead of doing the opposite of the negative 1 to 4, you could have done plus, go backwards through the negative interval, 4 to negative 1 of f of x dx. And then that would have given us the same A1 plus A2. So there's going to be more than one way to calculate total area. It's related to the definite integrals, and we just have to know that relationship. All right, I'm going to take the video, well actually let's do this examples 5, 6, and 7 here, and then we'll stop the video because this does have to do with this area problem. Now, there's a couple of things that we're looking at here. We are going to approximate, all right, so when we are doing an approximation, we're not going to do the limit. Like I'm going to be able to write down the limit definition for this, but we're not going to find an exact answer for this. We're going to approximate it. We're going to use 4 subintervals of equal length, And they want us to use the midpoint and the trap method, which is really, they're just playing with us because to do the trap, you're going to have to use your left and your right. So what we're going to do is we're going to say we're going to estimate the definite integral from 1 to 5, x squared minus 4 dx, using these Riemann sums. So this is section 5.6. This is called numerical approximations. So instead of taking this and using the limit definition, the limit as n goes to infinity of the sum I equals 1 to n of our delta x f of ci, instead of doing the long limit definition, we don't want to do that anyway, we're going to approximate what it is and using the Riemann sums. So let's start. I'm going to do the R4 first. So I'm going to go approximately using the R4. Now we might want to do some calculations. Our delta x, remember this is our A and B. So we're basically looking at f of x equal to x squared minus 4 on an interval of 1 to 5. Now one thing I might want to know before I start estimating this is this definite integral going to represent the area of the region, or is it going to only be the accumulation of area? So I need to look and see, well, what does this function look like? So let's do a quick sketch of our function. And so this is nothing more than a parabola that's been shifted down 4. So 1, 2, 3, 4. It has x-intercepts of plus or minus 2. So that's here. And since I'm going 1 to 5, I might as well go out and get the value for 5. So 3, 4, 5, 25 minus 4. So you're going to go up 21. And obviously I haven't left myself enough room, so we'll kind of wave our hands just a little bit here. That we're going to go off the edge of the page. And the area that we're interested in, well, not area, the section that we're interested in, and we'll assume I'm going off the page that I went all the way to the 5 here, is this area right here. Okay. Now obviously from just that sketch we can see that we're below and above. So this definite integral is not the area of the region. Okay? It is not going to be an approximate area of the region because this is not the total area. However, could some of these approximate? Well, let's take a look at it. Now, to set this up then, so what we're going to do is we need our delta x. So delta x, well I started it right there, so let's erase here, is going to be the 5 minus 1 over my n, which is 4. So this is going to be 4 over 4 or 1, so delta x is 1. And then we need to get our right endpoint, so maybe I'll list those over here. The right endpoint is going to be 1 plus 1i, so that makes it easy. So our right endpoint, the first one, is going to be 2, then 3, then 4, and then 5. So that one's fairly easy. We'll come back and calculate in a second what the actual value is that we get from the calculator. If I wanted to approximate with L4, delta x is the same. Now I'm using the left endpoint, so f of 1, f of 2, f of 3, f of 4. Okay, we'll calculate it in a second. If I use the midpoint between 1 and 2, f of 1.5, f of 2.5, f of 3.5, and f of 4.5. And I could do this by hand, or because I know my summation notation, what am I going to type into the calculator for each one of these? I could just plug in 2, get the y value, get my answer for this. I'm not going to show you them all, but I'll just really quick say, if you have this formula like this and you do want to plug it in, you could plug, say, this right one in by doing your summation notation. The sum, I equals 1 to 4 of my 1, which was my delta x, times the function, and my formula would be 1 plus I. So you would type in the sum I equals 1 to 4 of basically f of 1 plus I squared minus 4. So you could type that in, you could get your answers. All right, I'm just going to leave that for you to calculate. And then the last part is to get the approximation for your trap sum, which would be nothing more than to take your left plus your right and divide by 2 and get your answer for that. So I'm going to leave that because that's nothing more than just basic arithmetic calculations in your calculator, but I do want to answer the question that they ask above. Can any of these approximations represent the approximate area of the region? Now, when you look at these values that we have in here, this one is a negative function value, and so is that one right there. So R4 could be used because none of the f of ci's, they're always greater than or equal to 0 for each of those. So that would probably be an okay approximation of the area, but these would not be an approximation of the areas because they include values that are negative. Now let's take a look at example 6. What if instead of me asking you to approximate the definite integral using these numerical approximation methods, I ask you to approximate the actual area of the region? So I can still do that. We'll label it area of the region between y equal to x squared minus 4 and the x-axis on the interval from 1 to 5 is approximately. Now I can use the same R4 from above. Now I'm not going to rewrite it, we'll just import it. What would happen though to my L4? To do the L4, the problem is that that's a negative value, and I don't want to have area is always positive. So basically all you need to do is do the opposite of the value that's negative and then combine in. The rest of them are okay because they were positive. And again, I'll leave you to do the calculation. You could do your M4 as your approximation for your area, and again, the only change you need is make the y value that's negative positive, and the rest of them just bring along. And I will leave you to calculate. And then the trap method, again, the only difference is use the L4 and R4 from the area approximation here and here when you get this value to get those net numbers. All right, now, so keeping this in mind then, if I wanted to write integral expressions, some definite integrals that would give me the actual area of the region, what was most important, these are approximations, so now I'm kind of working toward getting an exact area of the region. Obviously I can't write 1 to 5 because that has some negative, some positive. So what we want to do is, what's the most important point? It's the place where it switches at the x-intercept. So the x-intercept on the interval 1 to 5 was x equal to 2. And so that's going to be our most important point. So I would say that my area on 1 to 5, the area of the region, and you can fill in the extra, is going to be the integral from 1 to 2 of this function. And, well, since I know it, I might as well put it in there, which was x squared minus 4 dx. And then, but that's a negative number, so I make it positive, and then I add the area from 2 to 5 on the function. And so we could do it by setting it up that way. But now that's not the only way that we can do it. There is another way to think about this. And instead of finding the x-intercept, determining where I'm positive or negative, what I can do instead is just make the function positive to start with. And how do we make things positive? We use absolute value. So I could take the integral from 1 to 5 of the absolute value of x squared minus 4 dx. And that would allow me to basically make it positive first, and then I would calculate the integral. Now, what are the advantages and disadvantages of these two methods that you have? I'm going to tell you that because, we're working toward, we don't want to always have to approximate these. We're approximating these above. We would like to be able to calculate these definite integrals exactly, and I definitely don't want to use the limit definition to do that. And what we're going to find out is that it's going to be very easy to calculate these definite integrals by hand. So easy to calculate by hand with shortcuts that we're going to be coming up with in the next few sections. This ends up being very difficult to do by hand because you end up with a composition in here and it's got the absolute value. So this one is what you would use when it's on the calculator section, because the calculator does not care whether or not you can integrate it by hand or not. The calculator is just going to do it. So this one is the one you would do on the non-calculator section. This is going to be the one that you are going to do on the calculator section because the calculator will take care of it for us. And so this is just a theorem that's just reminding us that if you are on a calculator, you always do this. Always. Could I have done it the method of find the x-intercept, determine positive or negative, write the multiple definite integrals? Yes, but that's longer. We're trying to be efficient and fast. So always, always, always on the calculator section, always use this method. Okay? Now, one last thing before we leave this set of notes and we start getting into some examples, let's kind of remind ourselves now that we have this idea of working backwards, let's remind ourselves that working backwards means that we're trying to find the antiderivative. So we want to start talking about some ideas that we had in Chapter 3. So this is a recall from Chapter 3. That if you had a function f of x, and f of x in this you're thinking of as your position function or your quantity function, that if f of x is differentiable, then you know that f of x is continuous. Because if it is not continuous, then it is not going to be differentiable. That when you have discontinuities like vertical asymptotes and jumps and holes, that is not differentiable at those points. So differentiability, if f is differentiable, you know it was continuous. If it was not continuous, then you know that at the discontinuities it's not differentiable. But then I want to remind you of the kind of golden rule that if I know that a function is continuous, it may or may not have been differentiable. Okay, so that's what we did back in Chapter 3. Now the trick here in Chapter 5, okay, so Chapter 3. So the trick here in Chapter 5 is that we're working backwards. The other trick is to remember that the f that I am talking about here, f of x, is the quote-unquote original function for Chapter 3. But in Chapter 5, when I'm talking about this function, f of x is your derivative. And so when we're talking about integrating it, we're basically saying we're working backwards from the derivative. Can we work backwards from this derivative? Now, what we know is that if the derivative, this function that we are talking about, is continuous, if we have a continuous derivative, then we must have a function that we could have that was also continuous as an antiderivative. Because if the derivative itself is continuous, the derivative exists for all values. And if the derivative exists for all values, then the function we started with was differentiable. The original function was differentiable. So the derivative function that I have can be integrated to work backwards. Okay? So if the function that is inside of the integral is going to be a continuous function, then I know that I can integrate it and work back, that it is a derivative of something that I can find. So continuity in the integration implies that you can integrate it. And that also means that if you can't integrate it, that means that it must not be continuous. Okay? Because if the derivative is not continuous, then you definitely know that, well, let's say it this way. If you know you can't integrate it, then you know that you can't be continuous. If there isn't an antiderivative, or you're having problems on this interval finding an antiderivative at each point, then there must have been a problem. And the problem was either because the function that you had originally had cusp or unusual steepness, or it was discontinuous. In either of those three cases, when you take the derivative will be not continuous. Okay? So that's those two facts. And then, but there's that gray area. If I were to look at this function inside of here and see that it is not continuous, does that always mean I cannot integrate it? The answer is no, because it will be sometimes. If it's not continuous, then I may be able to integrate it because I may be able to find an antiderivative that just had cusp or unusual steepness. So the antiderivative could exist, it just had cusp or unusual steepness. But if the other option is that if the f of x that's inside of here is not continuous, well, it may not be continuous because the antiderivative was not continuous, which means it's not going to be able to be taken an integral for it. Now, the nice thing for us is we're mentioning this, but we really only worry about this case in BC. And so that's kind of like, you'll see it next year in Math 201, that you are going to start taking a look at the ones that are the gray areas. If it is not continuous, can I integrate it, and how do I figure out whether or not I can integrate and get an antiderivative or not? So that's our BC and our 201 topic that we're going to look at. All the ones that you are going to look at, you are going to be able to integrate. Right? But we definitely need to know this, that if it is continuous, we can integrate it. And if we can't integrate it, then it's not continuous. All right? So I'm going to stop this video here and pick up and do the examples in the next one.